Alright, trick pre-cup. Here's an example about linear programming and optimization using inequalities. So here's the example. Here's the, what's that function called? The parent? Objective function. Here's the objective function up here. And here's the inequalities on the side. So I'll let you all copy that down, pause the video if you need to. But here we go. So first thing I notice when I do systems of inequalities like this with linear programming is that most of the time it's going to give you a basis like this. X is greater than 0, y is greater than 0. And when both of them are greater than 0, that means that we're working in the first quadrant, which is all that this graph gives us. But if you were to have a graph with all 4 quadrants in, this lets you know that you'll be dealing with only things in the first quadrant. Because we know that this is the line x equals 0, and everything is going to be greater than that. And then this is the line y equals 0, and everything is going to be greater than that as well. So we'll be working in this quadrant. Drew that line. Another one that's going to be really easy to draw here is going to be this x is less than or equal to 4. So that line obviously will just be x equals 4 that we draw. And if x equals 4, we're going to go to the x-axis, mark the number 4, and then this line means that x is 4 all the way, or for any y value. So we'll make this whole section x equals 4. And then if it's less than that, if x is less than or equal to 4, we know that it's going to be on the left side because these values are going to be less than 4, obviously. So we know that it'll be on this or in this section, but we have 2 more constraints to find as well. So this one is very clearly all divisible by 6. So we can divide this whole thing by 6. And that equation now is going to give us, I'll write it in blue right next to it, x plus y is less than or equal to 6. And that one's super simple. It's clearly not as complicated looking as this one. So we can put this into point slope form. Slope-intercept form. That's what it is. Slope-intercept form. We can put this into slope-intercept form very easily by subtracting x from both sides. And we get y is less than or equal to 6 minus x. And so the line that we draw here is going to have a slope of -1. It's going to have a y-intercept of 6. And so that's something that we can draw right over here. So we're going to have a slope of -1 starting at 6. So for each unit, we're going to go down and over to the right. And so here is what our line will look like there. A little squiggly, a little wavy, but that's all right. So now we know that y is going to be less than or equal to 6 minus x. And here's our y equals 6 minus x line. And so since it's going to be less than, we're going to think, in its y values, we're going to think lower than the line because it's less. So anything now to the left of this red line, in quadrant 1, and below this line are constrained values. But we've got one more constraint. And this one, we also are going to have to put into point slope form. Nope, slope-intercept form. My bad, again. So I'm going to do that in green right here. So we have x plus 2y is less than or equal to 10. So we get 2y is less than or equal to 10 minus x. Divide both sides by 2. And we get y is less than or equal to 5 minus 1/2 x. So for this one, in slope-intercept form, we've got the slope and we've got the y-intercept. So we can easily graph this one as well. Our y-intercept is going to be 5, We'll mark that here. And our slope is -1/2. So every time we go down 1, we're going to go to the right 2. So our first intersection point is going to be here at 2, 4. And then our next point will be 4, 3. So on 6, 2. But as we come out farther this way, we're not even working with our area of constrained values anyway. So it's not really worth finishing this line. But it's definitely worth drawing in right here. So there's a line, y equals 5 minus 1/2 x. And we know that y is less than this line. So again, we're going to be working with y values lower than this, and y values lower than that are below the line. So we can go through this and shade only the region that fits all 5 of the constraints, all 5 of these. So we can eliminate this already, right? Because x is not less than 4, less than or equal to 4, right? And then likewise, we can eliminate this section because y is not less than or equal to 5 minus 1/2 x in this zone. But we're going to stop right at this vertex because the y equals 5 minus 1/2 x line is the one we're going to erase because now the values in this section don't fit under the constraint y is less than or equal to 6 minus x, which is this blue line. So we know that our constrained values here are going to be in this shaded region. And then these are the only values that we can find our max and min from. And like I've said in the original video, our max and mins are always going to be found from vertex points. So we're going to keep note of the vertex points right now. Got one there. And a vertex is anywhere where 2 objects meet. And we're specifically looking at where 2 objects meet in this figure. So a vertex wouldn't have been over here where the 2 lines met. We're more talking about the vertex or the vertices in this figure. So we've got one here, got one here where 2 objects meet, got one here, and then lastly we got one here. And so maybe note that you've got 5 vertices, 5 equations, because similarly if you only have 4 equations, you're only going to have 4 vertices. So that's something to note as well, something or an easy way to keep track of that. So now we're going to test all these vertices in the objective function because we're looking for the maximum value of z. I should probably find that. Max value of z. Okay, so that's our task. That's usually going to be our task for problems like this. So keep that in mind when we're doing this. Sometimes the minimum as well, but we're only going to do the maximum here. So we're going to take these vertices. We're going to give them each coordinates. So we know that this one's 0, 5. We know this one's 2, 4. Here we got 4, 2. Got 4, 0. And lastly, we've got 0, 0. I'm going to take a guess and say that 0, 0 is probably not going to be our max vertex because I look at this and 0, 0, z equals 0 doesn't sound like a very high maximum. And also this point is the farthest to the left and the farthest down that we can get in this graph. But we can test all of these out. So we have 4 times 0 plus 5 times 5. We have 4 times 2 plus 5 times 4. 4 times 4 plus 5 times 2. And 4 times 4 plus 5 times 0. And so these are the vertex points that we're working with. We've got x values and y values of the vertices. And so from here we can just calculate this, and whichever one of these vertices has the highest value for z, So whichever one of these expressions has the highest value, that's going to be the maximum, and the maximum point is going to be at that coordinate. So we'll do this quick. 4 times 0 plus 5 times 5 equals 25. 4 times 2 plus 5 times 4 equals 28. 4 times 4 plus 5 times 2, 26. And 4 times 4 plus 5 times 0, 16. So, as we can see, 28 is going to be the max value of z, and at the coordinate 2, 4. So right here, that's going to be the max value. We'll say that the max value is 28 at point 2, 4. And so that's how we're going to write our solution. If you can see that over here. So we've got the max value of z equals 28, and then we're going to clarify at which point is that true. So I'll give you the answer right here in red. That's what you should have gotten there. Here's our constrained value section. Here's our inequalities. Here's some work we got. So I think y'all will be pretty good with linear programming and systems of inequalities like this. If you have any questions, obviously let me know in class. But you should have a good handle on this, and it's mostly just keeping your information straight and finding what the question is asking for. But that completes it for this example, and I'll catch y'all soon.